And in chapter number 1, the title of the chapter is What Are We and How Do We Know? And it may strike you as something strange. People always ask, who are you? But what are you? Or what are we? Maybe it will become clear as we move on. We always start chapters with a guidepost. And the guidepost is basically, it sets you to what we're going to encounter in the chapter. And here it says, as you study astronomy, you will learn about yourself. You are a planet walker, and you should understand what it means to live on a planet that whirls around a star, drifting through a universe of stars and galaxies. You owe it to yourself to know where you are. That is the first step to knowing what you are. In this chapter, you will meet 4 essential questions about astronomy. Why should we study astronomy? How do scientists know about nature? Where are you in the universe? And how does human history fit on the time scale of the universe? Besides learning about astronomy, you will consider important questions about science. How do we know? How does science work? How do we know? What is the difference between a scientific argument and advertisement? And what we plan to do in this chapter is we're going to take you through a cosmic zoom, roaring outward through the universe, checking out its major features. And of course, in the next chapter, we'll try to look at Earth and how Earth basically moves around the sun and how you view the sky of the Earth. So that's what we try to accomplish in this chapter. Of course, you will encounter some scales of time and sizes that you are not familiar with, because you're going to look at things that are not on the Earth here. You're going to look at the moon, you're going to look at the sun, then you're going to look through the galaxy, and we're going to encounter units which we call astronomical units and light years and so on. So that's something that we have to use when we try to measure things in the universe. So we'll start with a scene that you're familiar with, okay? And this scene here, it's a campus scene, and the area is about 16 by 16 meters. And a lady is basically sitting here, okay? So you can look at this lady here, where she's basically sitting on the chair in an area which is about 16 by 16 meters, which could be the size of a small home. And what we're going to do next is basically we're going to zoom outside. That means we're going to go up. And you know, when you go up, things will look small. And what we're going to do is we're going to zoom by a factor of 100. Meaning, if I want to zoom by a factor of 100, in the previous, I had 16 by 16 meters. Now I want to zoom by 100. That means I want to go up to see a bigger area. That means I'm going to multiply this by 100. And that will be 1600 by 1600 meters, and this is basically 1.6 by 1.6 kilometer. Okay. So you're basically seeing probably the size of our university. Okay. So if we go up, all what we had in the previous slide here, now it will become a very small point in a city, a view like this, which is about 1.6 kilometers by 1.6 kilometers. Now we can also zoom out by a factor of 100, which means if I multiply 1.6 by 100, it will give me 106. So now, if we do that and we zoom out by a factor of 100, and we get basically 160 by 160 kilometers, the part of the city that we had in the previous slide, it will be basically coming some point which is very small in this location here. 160 kilometer, it's like the city, it's like the distance between Al Ain and Abu Dhabi. So since we are still on the surface of the earth, we can basically look at an area, and we can take an area of 160 by 160 kilometers. So now if I ask you, what is the, or how big is the lady that we have in the first slide? Okay. And you're going to tell me that you're not going to see that lady anymore because you are high enough to see a bigger area. And that lady now is not clear anymore, not even probably the city itself where the scene was taken. Now we're going to ask question, how much time does it take to cross this distance? And bear with me, this will become clear why we do this. Okay. Because later on you will learn that when you look at things in the night sky, you're not seeing them right now. You're basically seeing them in the past. You're all familiar from your school days that if you take the speed, it's equal to distance divided by time. Okay. That's basically the speed. Now, if you want time, of course, will be distance divided by speed. That's what time is. So now, since the distance that we're talking about here is 160 kilometers, and if you take the a car which can travel at 100 kilometers per hour, and you divide 160 kilometers by 100 kilometers per hour, that will give you around 1.6 hours to cover that distance. Now, if we take a plane and the plane can travel at 900 kilometers per hour, it will cover that distance in about 10 minutes. Now, if we look at a rocket, the rocket basically covers the distance. If the rocket has a very high speed of 10,000 kilometers per hour, it will take about 1 minute. Now, light, which is something that we need to see things, light has a very high speed. It has a speed of 300,000 kilometers per second. That's how fast light is. And the distance of 160 kilometers will be basically covered by light in 0.0005 seconds. So it's very fast. And that's why if you're communicating with mobiles and so on, it uses microwaves that can travel at the speed of light, so you do not experience any delays. Now we're going to basically zoom further, but we're not going probably now. We're going to look at the whole planet Earth, and we're going to look at the diameter of the Earth is about 12,756 kilometers. That's the diameter of the Earth. Diameter meaning from one end to the other end. That's the diameter. It's not going around the Earth. That's just the diameter. Now, if you look at what we had in the previous lecture, previous slide, this whole big area now became a small part here on the on a planet Earth. There are a few numbers that you have to memorize, but not everything. But you should know that the diameter of the Earth is around 12,800 kilometers. Okay. Now, again, if I want to cover this distance here, which is 12,756 kilometers, which is the diameter of the Earth. Now, if I want to do that with a car, which can basically travel at a 100 kilometers per hour, it will take about 5.3 days, assuming that you never stop, you never take breaks, and so on. A plane which can travel at 900 kilometers per hour will take about 14 hours, and that's anyone who experience taking a plane from here to North America, let's say United States or so on. It takes that long. A rocket, which can travel at a very high speed, which is 10,000 kilometers per hour, it will take about 1.3 hours. But light, again, has a very high speed, which is about 300,000 kilometers per hour, 300,000 kilometers per second, which is a very high speed. It will take about 0.043 seconds. So it's very fast. And again, that's also for our communication. That's why we do not feel any difference. We're going to continue with this analogy to show you that you will encounter time delay basically when you go to higher and higher distances. So now what we're going to do next, we're going to go high enough to see the Earth and the Moon orbiting the Earth. Now the distance between the Earth and the Moon is about 384,000 kilometers. It's a huge distance. And that's why sometimes you can cover the Moon with your hand from here. But the Moon is not that small, but it looks small because it is very far away from here. Now, if I want to use the analogy of how much time it will take a car to go from here to the Moon, and assuming that there is a road that the car can travel on, it will, if the car maintains a speed of 100 kilometers per hour, it will take 160 days to do that. And a plane will take about 18 days. And of course, planes need to have an atmosphere. They need some air to travel through. And as soon as they get outside the atmosphere of the Earth, they're not going to be able to do that. But assuming it will, if we basically imagine, it will take about 18 days. A rocket will take, if it travels at 10,000 kilometers per meter, it will take about 1.6 days. And that's why usually if you want to travel to the moon, you have to do that in terms of days to get there with special ships and rockets and so on, spaceships. Light, which has a very, again, high speed, which is 300,000 kilometers per second. And this is the highest speed that we have in our universe. The light basically will take 1.3 seconds to cover this distance. So when you look at the moon, you are not seeing the moon right now, okay? You're actually seeing the moon 1.3 seconds away ago. So you're not actually seeing the moon in real time. There is a time delay. Whatever, when you look at the moon, you're not seeing it right now. If you want to know what the moon is right now, you have to wait for another 1.3 seconds. So for example, if someone is at the moon and wants to communicate with us here, and he or she sends a signal at the speed of light, the signal will take 1.3 seconds to reach us. And our response, which we're also going to send at the speed of light, will take another 1.3 seconds. So the answer for him will be after 2.6 seconds or 2.5 something, okay. Well, roughly speaking, 2.6 seconds. So there is a time delay now. When you basically try to look at the moon or you try to communicate with someone in the moon. So now you can basically see where we're going with this analogy that we started with. Now we know that the Earth revolves around the sun. So now you want to go high enough to basically look at the Earth orbiting the sun. And the sun will be here, and of course the Earth will be here. Now the distance between the sun and the Earth, it's about 150,000 kilometers. 150 million kilometers. It's a huge distance. Well, of course, with this, you're not going to see, if you look at what we had in the previous, you can basically see the moon orbiting the sun. But here they become as one point because the distance between the Earth and the sun is just a huge. Of course, we'll talk about the solar system. Next to the sun is Mercury, and then after that you have Venus, and then after that we have Earth, which is our planet. But the Earth is the distance, or the average distance between the Earth and the sun is about 150 million kilometers. Now, if we want to use the same analogy, where we say that we're going to take a trip from here to the sun using a car at an average speed of 100 kilometers per hour, it will basically take you about 171 years, which is not, it's something impossible for humans to do. And of course, we do not have highways to do that. And the temperature at the surface of the sun is about 6,000 degrees. So it's not something that you can withstand. A plane will take 19 years to accomplish that. A rocket, which can travel at a speed of 10,000 kilometers per hour, will take 1.7 years. Again, that's a very long time. You really have, that's why when once we send the probes to study the sun, we have to wait for a long time. Now, when we talk about light, which basically has a high speed of 300,000 kilometers per second, light will cover this distance in about 8.3 minutes, roughly speaking. Which means when you look at the sun, you are not seeing the sun right now. You're actually seeing the sun 8.3 minutes ago, not right now. So just for the sake of argument, if there is something at the surface of the sun and it's trying to communicate with us and it sends a signal at the speed of light, the signal will take 8.3 minutes to reach us. And our answer, if we send it at the speed of light, the response also will take 8.3 minutes. So whatever it's there, it will get the response from us 16 minutes or 16.6 minutes from the initial or from initiation of the communication. So there is a huge time delay now. So remember, when you look at the sun, you're not seeing the sun right now. You're actually seeing the sun 8.3 minutes ago. We see things because of the light that comes from them. And since the sun is about 150 million kilometers away, now, okay, when you look at the sun, you're not seeing the sun right now. You're seeing the sun in the past. If you want to basically get, let's say, an image of what the sun is right now, you have to wait for another 8.3 minutes to get that. Is this point clear? Again, if you have any questions, you can chat, you can use the mic as well, and you can interrupt me. Okay. So now you know why we're going with this analogy. So when you look at the moon, you're not seeing the moon right now. You're seeing the moon 1.3 seconds ago. When you look at the sun, you're not seeing the sun right now. You're actually seeing the sun 8.3 minutes ago. So now we're going to introduce a new unit. And this unit, we're going to call it the astronomical unit. We're going to call this the astronomical unit. Okay. And this astronomical unit is equivalent to the average distance between the Earth and the Sun, which is 150 million kilometers. So if we want to continue using the unit of kilometer as a unit of measure, when we're actually measuring things within the solar system, how far is the Sun, how far is Venus, how far is the Earth, and so on. Now we're going to use the average distance between the Earth and the Sun as a unit, and we call that astronomical unit, so we call it AU. So 1 AU is equivalent to 150 million kilometers, or we can say it's also equivalent to the distance traveled by light in 8.3 seconds. So now in the solar system, or measuring things in the solar system, we're going to use the AU unit. Is this clear? Any questions so far? And that's basically if you go high enough to see the Earth orbiting the Sun. Just to give you an idea, and we'll talk about that in chapter number 8 when we talk about the Sun. This is the surface of the Sun, and what you see here is basically big arches that coming from the Sun, and this is basically the Earth, to show you how small is the Earth relative to the Sun. And if you go right now outside, you can feel the heat out there, and the source of that heat is basically coming from the Sun, and the Sun is about 150 million kilometers away. That tells you that the Sun is very active. And I told you, I think the surface temperature of the Sun is around 6,000 degrees. In the core of the Sun is about 14 million degrees. So if you get to the surface of the Sun, you will basically become vapor. Now, this is basically how the Sun looks like, and we'll discuss this in chapter number 8. That's basically a filter that we put there to see something that we call a granulation on the surface of the Sun, and some activities that we see on the Sun. But that's basically how the Sun looks to you when you look at it at any day. And of course, I don't advise you to look directly at the Sun, because this will harm your eyes. Now, the Sun itself is white, by the way, but due to the atmosphere of the Earth that we have here, that's why we see this yellowish color. But that's how the Sun looks to us. And sometimes you can cover it with your hand in here, but the Sun, actually, you can fit more than 1 million Earth in the Sun, just to give you an idea of how big the Sun is. You can fit 1 million Earth in it, okay, just in the size of the Sun. Okay. No, the Sun is not smaller than the Earth. The Sun is huge, but it is 150 million kilometers away. And the further things are away from you, the smaller they look to you. You can experience that by yourself, okay? When you're coming into a city, and as you approach and approach, things will become bigger and bigger. Okay. Now, next to the Sun, you have 2 planets. The first one is Mercury. And Mercury basically has a very light atmosphere, and of course it's at the mercy of the Sun. And then you have Venus, and Venus has a very thick atmosphere made of sulfuric acid, and that's why it becomes very luminous. So what you see here, you see a very thick atmosphere that we are not able to see what's on the surface of Venus. So you go the Sun, and after the Sun you have Mercury, and then after Mercury you have Venus, and then after Venus our planet Earth, and of course around the Earth we have the Moon that orbits the Earth. Now, how about if we want to go with the same what we started with, we zoom by 100, which means we're going to go further by 100. Since the Earth to the Sun is 1 AU, so we're going to look from a distance about 100 AU. So again, if you look at what we had in the previous slide and you take it into this one here, now you can see the whole solar system. Now, of course, the orbit of the Earth will become very small here, and then you'll have Mars, Jupiter, Saturn, Uranus, Neptune, and you see all of these planets. And at the end here, you have Pluto, but Pluto is no longer considered as a planet. It's considered as a dwarf planet. So if you go further from the Earth here, about 100 AU, then you're going to be able to see the whole solar system. Now, if we continue with the analogy of how much time it will take by car, by plane, by rocket, a rocket will take 171 years, which is something is not feasible during a human's life. Light will take 14 hours. So imagine if we send someone in a ship and they're very close to a distance of about 100 AU away from us, and they send us a signal to communicate, and they can send it at the speed of light, which is the speed of light, which is the highest speed that we have in our universe. It will take 14 hours to reach us, and our response will take another 14 hours. So they will get an answer after 28 hours. Meaning they are on their own. Okay. When they're out there, they really have to be able to do things on their own. Now, of course, if we try to look at the members of what we have in the solar system, we look at the red planet, which is Mars, and you know that United Arab Emirates sent the Hope probe orbiting Mars to collect some information from there. These are high quality images that we can see for Mars taken previously with other probe. You can see that there is some sort of canyons there and rivers, and some assume that maybe Mars at some point had running water on its surface, and running water is essential to life. That's basically the surface of Mars. Of course, there is a probe that reached there and tried to look at some features on Mars, and now even United Arab Emirates has a probe, the Hope probe, that's orbiting Mars and trying to understand the atmosphere of Mars. And there are other vehicles that had reached the surface of Mars, and they try to understand as much as we can about Mars. Next, when you go further, you will see Jupiter. And Jupiter is the biggest planet that we have in our solar system. Now, there is a feature here, and we call this the Great Red Eye. And this is, as a comparison, that's the Earth. Just to tell you that how big is Jupiter relative to the Earth. But Jupiter is not a rocky planet. Mercury, Venus, Earth, and Mars, they have rocky surfaces, solid. But Jupiter and out there, they are basically made of gases. You cannot stand on their surfaces. Okay. They call them gas giants. Okay. And there is another word that we're going to use in chapter number 6. We're going to call them Jovian planets. Again, this is basically Jupiter, and this is one of the moons that orbit Jupiter. There are 4 moons that can be seen with a crude telescope, but I think Jupiter has about 76 moons or something like this. It has lots of moons on it. But the ones that we can see with a telescope, and I think we'll talk about that in chapter number 4, when Galileo Galilei made a telescope and looked at Jupiter, he saw what we call the 4 Galilean moons. They call them Galileans because he was the first one to spot them. Okay. Then after Jupiter, we have Saturn, and Saturn has a beautiful ring around it. بالعربي نحن نقول له زحل. Okay. And you need a good telescope to see this. Okay. But that's next to it. And then Uranus and Neptune. And then finally, you come to Pluto. Okay. And Pluto, there is a probe called the New Horizon, and it reached Pluto in 2015 around July, and start going around Pluto. And it took some images of that. I'll try to see if I can get some of these images for you. So it's basically start scanning some areas and try to get something of the surface of Pluto. And then it left Pluto and moved somewhere else. Okay. And its journey. But Pluto is small enough, and there are others like Pluto, and now since 2008, Pluto has been regarded as a dwarf planet. A dwarf معناها قزم بالعربي. Okay. So if we look at our solar system, you have the Sun, and then Mercury, Venus, Earth, and Mars. We call these the 4 inner planets, and these planets they have rocky solid surfaces. And then the 4 outer planets, which is basically Jupiter, Saturn, Uranus, and Neptune. These are the gaseous planet or Jovian planets, and Jupiter is the biggest planet in all of these. And then you have Pluto. And I told you Pluto is now considered as a dwarf planet. And this, it just gives you relative sizes. So you can see where Mercury is, Venus, Earth, and then Mars. Sometimes Venus and Earth are regarded as sister planets because they are incomparable sizes and so on. And then you can see Jupiter, how big Jupiter is. Of course, the Sun is much bigger than that. That's why we're only using a portion of the Sun. And then Saturn, Uranus, and Neptune, and so on. And you can see Pluto as a dot there. Okay. That will give you an idea of the relative sizes of these planets within the solar system. As you can see here, you can see the Earth, Venus, Mars, and then you can see different moons. That's where Mercury is. There are some moons orbiting Jupiter and Saturn, which are much bigger than our moon, or basically even Mercury. So that just gives you an idea of relative sizes of things that we have within our own solar system. And finally, all these planets orbit the sun in something that we call the ecliptic plane, meaning these basically orbit in a disk-like. You don't see them going up and down this way. They're all like in the same plane. And we call this the ecliptic plane. And we'll explain what the ecliptic is in chapter number 2. When we talk about the ecliptic, it's basically the orbit of the sun around, the orbit of the earth around the sun. So you can see the earth orbiting the sun, and all of them basically are in the same plane. They're further, but they seem to be, when you look from the side, they look like a disk to you. And you can see here, the closer, the fastest, the further, the slowest. And that's basically the motion of the orbits of the planet around the sun. And we say the moon is orbiting the earth, is also in the same plane, which we call the ecliptic plane. Okay. So that's basically how we look at this. Okay. So you live in a solar system. It contains all of these planets. These planets basically orbiting the sun, and they rotate around their axis. And we'll talk about this later. Okay. So here, for example, when we talk about the Earth, we know that the Earth is revolving around the sun and it's rotating around its axis. But these will become clear later on. We just want to survey things. Now, let's move further. And we want to zoom out by 100. That means we're going to take 100 and multiply by 100. That will give you around 20. It will give you 10,000. Okay. Now at 10,000 AU from here, you're not going to see the solar system, but you can see the sun, okay, glowing. And that's now a huge distance from here. Now, if we look at light and how much time needed for this distance to be traveled by light, it will take about 60 days. So if a ship left the Earth and it is at this distance here, and it sends us a signal, the signal will take 60 days to reach us. And our response will take another 60 days to reach the ship. And that will be a delay of 120 days. That means whoever is in the ship, they have to be capable of doing things on their own. They don't have to wait for our help or wait for our explanations. Now, what happens if we want to go out further? And now we're going to introduce something that we call a light year. We'll explain what a light year is. But now when you use this light year, that's 17 light years, while the sun is here, and you see a few other stars around the sun. Of course, you're not, if I ask you about the lady that was in the first slide, this is basically nothing. Okay. It's like looking at a grain sand in the desert. Okay. Even smaller than that, way, way smaller than that. So what is a light year? Now, a light year is a measure of distance. People hear year and they think it's time. But right away, when we say light year, that means we're talking about a distance. Meaning that we're looking at the distance traveled by light in 1 year. And if you want to do that, remember when we said that V is equal to D over T. Okay, so D will equal to V multiplied by T. Okay, so now we're going to multiply the speed of light in 1 year, and the speed of light is 300,000 kilometers per second. The year, it has 365.25 days. Remember, every 4 years we add a day, and each day is you have 24 hours, and each hour you have 60 minutes, and in each minute you have 60 seconds. Because you want to eliminate the second that we have here, so that will give you about 9.5 times 10 to the 12 kilometers. And when we say 10 to the 12, that means 1 and 12 zeros in front of it. That's a huge distance. So we say it is roughly about 10 raised to the power 13 kilometers. That means 1 and 13 zeros in front of it. That's the distance that it traveled by light in 1 year. So, which we call 10 trillion kilometers. Now we can do that in meters, and you know that when you talk about a meter, a kilometer has 1,000 meters. So you'll add another 3 zeros to this in meters. So it will be 16 zeros, but you change from a kilometer to a meter, and that's why we say it is 10 raised to the power 16 meters. So many times you hear that a light year is 10 raised to the power 16 meters, or the distance traveled by light in 1 year. That's what a light year is. Now, when we look and we ask, relative to our sun, what is the closest or the nearest star to us? And the nearest star to the sun, it's called Proxima Centauri at 4.2 light years. Meaning, when we look at the star, we don't see the star right now. We see the star 4.2 years ago. That's the closest neighbor to the sun. And you should basically memorize this name here. Proxima or Proxima Centauri. Okay. 4.2 light years away from the sun. So a light year is the distance traveled by light in 1 year. It is 10 raised to the power 13 kilometers. It is 10 raised to the power 16 meters, or 63,000 AU. Just to tell you how huge this distance is. So for example, if someone or a ship is 1 light year away from us, and they want to communicate, they will send a signal. They will send it at the speed of light. It will take 1 year to reach us. And our response will take another year to reach the ship. So it will be 2 years if they are waiting for answer from us. Or if they have a newborn baby there and they send us a photo of the newborn baby. When the photo reaches us and we look and we say, oh, what a cute baby, the baby is 1 year old. Okay. And that's why I told you, when we use this analogy, I told you have to be careful, because when you look at the night sky, you are not seeing things right now. You are basically seeing things in the past. So for example, if we want to travel to this star, okay, if we use a spaceship that can travel at 60,000 kilometers per hour, it will take us 80,000 years to reach there. Of course, this is not feasible during our human life. We need something that can travel at the speed of light. We need a breakthrough to reach Proxima Centauri. And of course, in the night sky, you see a huge number of stars. All of these stars that you basically look at, they are basically at different distances from here. One star might be 10,000 light years away, another is 600 light years away. So when you look at the night sky, you are not seeing things now, you're seeing them in the past. You don't know what they are right now. The things that you can basically say, ah, yes, I can relate to them is the moon 1.3 seconds ago, the sun 8.3 minutes ago, but stars, no. Okay, stars, when you look at the night sky, you're basically seeing things in the past. We use here a bouquet of flowers to show you that these stars basically come in different sizes and colors and so on, and we'll discuss that in chapter number 9. So if we zoom again by 100, since we had 1.17, so we can take 1,700 light years, and at that you will see a huge number of stars. And then if you basically go further, and we'll talk, I will give you, if we can see that, something called the Orion Nebula and so on, that I may actually ask you to look at. You can look through our galaxy and you will see a huge amount of gas and dust and stars. Now, our own galaxy has a diameter of about 100,000 light years. So you're talking about huge distances here. And by the way, it could extend to 120 light years, at 120,000 light years. So it's something very huge. Of course, what you see here in the slide is artistic rendition. That's what we think our galaxy looks like, because we collect, and we'll talk about energy and light and so on in chapter number 5 and how we deal with it. So that's basically our own Milky Way galaxy. It is vast. And this Milky Way galaxy contains something between 200 to 400 billion, okay, stars. Billion. And a billion is 9 zeros in front of it. So you have a huge number of stars in our own Milky Way galaxy. And one of these stars is the sun. And around the sun happens to be a planet, and one of these planets is Earth, and around Earth, on Earth, humans live. So now people say, why should we be the exception? Maybe there are other solar systems, and maybe there are situations like ours, and maybe there is life out there. But it will be what form of life? And that's why at the beginning we said, what are we? It's not who are we. If there are other planets somewhere orbiting other stars and they have some intelligent life. What form of intelligent life? Okay, so the question is not who are you, it's what are you? And we all know here on Earth that before us we had dinosaurs that lived before us. Okay. So that's why that question that we asked at the beginning. Now, this is the Supramu galaxy. We can see these in the atmosphere, and that's basically in the universe. And that's how we concluded how our galaxy looks like. In chapter number 10, we'll try to address the different type of galaxies and so on. I will take it from here in the next lecture, but I will deal with any questions if you have any. Do you have any questions? Do you have any questions? It's all clear?